Our next speaker is Paul Sutton, and he'll be talking about OpenFirst, the open SDR LTE platform for first responders. Thank you.
Thanks, Derek. Good morning, everyone. I'm Paul Sutton. I'm from a company called Software Radio Systems, and I'm going to talk a little bit about a project we have called OpenFirst at the moment. So I'll start off by telling you a little bit about the company, who we are, what we do, a little bit of background, and then I want to go into the OpenFirst project itself, what it consists of, what we're planning to do, and how we're planning to do it. And then I'm going to talk about SRS LTE, which is our code base, our open source code base, on which OpenFirst will be built. So starting off with Software Radio Systems, who are we? We're a small company. We're a spin-out from Trinity College in Dublin in Ireland. We've been in business since about 2014. We've grown quite a bit over the last 12 months. We're 8 people in total now. We have offices in Cork and Dublin in Ireland and in Barcelona in Spain, so we're pretty spread out. What do we do? We started off as a company doing general software radio work. As time has gone on, we've become more and more focused on LTE. So while the web page says Satellite Systems, IoT, and LTE, really we're fully focused on LTE at the moment. If you've heard of us, you've probably heard of us because of SRS LTE. And this is our open source code base for LTE implementations in SDR. This has been around since about 2014, 2015, and it's grown over time. So it started out as a DSP library for LTE PHY implementations and testing. In 2015, we added a full UE application stack. This is so not based on GNU Radio. It's a standalone application, but supporting most off-the-shelf SDR hardware platforms. So our go-to platforms at first were the USRP series. So when we released the UE, this meant that you could run a full UE stack on a standard x86 platform with a B200, B210 front end on that. And it was fully functional, so still is. You can connect to commercial base stations and run full throughput at 20 megahertz. And open source really has been a big aspect of what we've done from the outset. And it was interesting to listen yesterday to the discussion around business models for open source and monetization for open source. And as the various options were listed, I was mentally checking them off and thinking, yeah, we've done that, we've done that, we've done that. And one major aspect, which I don't think was mentioned, but which was key to us as a company, was R&D projects, publicly funded R&D projects. And while these obviously don't form a business model in themselves, they're key to creating a successful company around open source. So if you're thinking of creating a company around open source, chances are you're not going to get VC funding to do that. And you're going to have to bootstrap that. And an excellent way to bootstrap that is through R&D publicly funded research projects. These are a couple of the projects we've been involved in. We've worked with the European Space Agency and through European funding programs like FP7, Horizon 2020. Some of these projects are focusing on things like hybrid satellite and terrestrial transceivers. We've got Flex was focusing on NB-IoT when that flavor came out in LTE. Osmosis is looking at media streaming over hybrid satellite and terrestrial networks, and so on and so forth. But of course, as well as those types of R&D projects, we have a number of commercial projects ongoing. So just picking one of those that's reasonably interesting is with a company called Smart Sky. So these are a company who are rolling out a 4G network for air-to-ground connectivity for business jets, largely across the US. So they're rolling out that network at the moment. These guys took the 4G standard and tweaked it to allow it to work well in that scenario, in that air-to-ground scenario. And where we came into the equation was when they started looking for test equipment. So you can't buy off-the-shelf test equipment with their custom modifications. They came to us with specific requirements, and we've been building custom test equipment for them for the last 12 months. And that's been a really interesting project for us. So that's a quick overview of who we are. So the OpenFirst project, what is it? Where did it come from? What do we plan to do? So the OpenFirst project is funded under the Public Safety Innovation Accelerator program. So when the AWS-3 transition happened and Spectrum Auctions raised a huge amount of money, $300 million of that was set aside for public safety R&D and was provided to NIST, to the National Institute of Standards and Technology, to set up a program to spur innovation and investment in public safety communications. So the Public Safety Innovation Accelerator Program was announced in December last year, and the first 33 projects kicked off in June of this year. So overall, there were 38.5 million allocated among those 33 projects. And they spanned topics from location-based services, mission-critical voice, public safety analytics, LMR to LTE, and underlying all of these themes was an interest in R&D platforms. So the funders were looking for funding or R&D platforms which allowed them to test and implement some of the new features that are coming out in LTE, specifically of interest for public safety. And that's what OpenFirst is all about. So what we're proposing to do is to develop an open source end-to-end LTE network for public safety research and development. So this consists of the UEs, the eNodeBs, and the EPC. The idea is to have a reference implementation of some of the key LTE features that are of interest for public safety. So these include multicast, device-to-device, priority, and so on and so forth. The idea here is to enable and support and grow the public safety broadband development ecosystem, but they're also very interested in providing a commercialization path for public safety LTE using existing business models. And we're going to build this based on the SRS LTE suite of open source software, and we've already started doing this since June of this year. In the project proposals and in the request for proposals, a number of key requirements were set out, and I thought these were quite interesting. So for the R&D platform, some of the things that we're looking for were sufficiently complete implementations, sufficient sets of components, performance comparable to likely operational implementations, getting to network scale, path towards operational implementation. But then there were also more general requirements like ease of use, clarity and completeness of documentation, long-term sustainability, the availability for follow-on research, and potential for commercialization. And one of the nice things about having an open source platform is that you can tick an awful lot of those boxes. So in ease of use and availability and sustainability, you're immediately winning with an open source solution. And SRS LTE has been open source under AGPL 3 since the outset. So where are we at right now? This is a very rough estimation of the status of each of these parts of the puzzle. So SRS UE has been around for the longest. It's probably the most stable application that's out there. SRS eNodeB was just released. The first release of that was in June. And it's fully functional, so you can run SRS eNodeB, connect a commercial off-the-shelf handset, run full throughput at 20 megahertz. We're planning another release for the end of this month. We're going to be improving the stability, fixing a lot of bugs in that, and so on. And SRS EPC doesn't exist yet, but the first release of that is going to be before the end of the year. So the target is that by the end of this year, you'll have the full network from end to end available as open source in a single repository, git pull, build, and you've got a full network implementation on your desk for R&D. So building on from that baseline end-to-end network, what are we proposing to do? So as I said, the real purpose of this project is to implement some of the key features that the LTE standard is proposing for public safety. Things like priority, preemption, and quality of service, proximity services, eMBMS, and so on. So we're structuring the project in 4 phases over 2 years. So by the end of this year, we'll have the baseline end-to-end network consisting of the EPC, the eNodeB, and the UEs. The first 6 months of next year, we'll be focusing on release 8 and 9 feature sets. So we'll be looking at eMBMS support. That'll probably come in a little bit earlier. Measurement, handover, mobility, this kind of support. Then towards the latter 6 months of next year, we'll be looking at things like MIMO, carrier aggregation, and starting to work on device-to-device on ProSay. A lot of these are actually coming through a little bit early. So eMBMS is going to come in a little bit earlier than that. 2x2 MIMO, TM3 and 4, they're going to be in place before the end of this year. So you'll probably see them a little bit sooner. So that's the project, and now a little bit about SRS LTE itself, so the software suite, what it consists of, and some of the technical design choices involved in trying to implement LTE in software radio. So first off, why the interest in implementing LTE? And it's a very, very interesting standard. It's the fastest growing mobile telephony technology in history. The scale of it is staggering, and the number of active deployments, it's pretty much ubiquitous, which makes it very, very interesting from a researcher's point of view. It means there's always a live network to play with. And an interesting use case of this was when we started working in NB-IoT. So NB-IoT was the machine-to-machine flavor of LTE that was brought out. It was released, I think, in the middle of last year. And just before Mobile World Congress in February of this year, Vodafone switched on NB-IoT carrier in-band in one of their on one of their base stations in the center of Barcelona. And we were able to start working with that immediately and start testing out our NB-IoT receiver and NB-IoT analysis tools directly on that waveform, which is very, very interesting. It's also a very, very complex standard. So the level of complexity is pretty staggering. The physical waveform itself is this multiplex of a huge number of different physical waveforms mapped onto a standard time and frequency grid. So that makes it very, very challenging, but it also makes it very, very interesting. These are some of the flavors of physical waveforms that get mapped onto that resource frame itself. So it's pretty much across the board, both in the downlink and in the uplink. So a quick primer on LTE, on the protocol stacks and what's involved in trying to build this. So the physical layer, this is the UE network, UE protocol stack from PHY up to NAS and IP. And you can split the stack in control and data. So the control plane is moving up through MAC, RLC, PDCP, RRC, and NAS. And then the user data plane is moving up through IP. So it splits at the top of the PDCP. And what are each of these layers doing? So the physical layer is very, very flexible, as I said, OFDM in the downlink, SCFDMA in the uplink. I'm sure most of you here are very familiar with it. At the MAC layer, so you're prioritizing and multiplexing the logical channel data. It's responsible for scheduling. It's responsible for link adaptation. It's responsible for HERQ. So HERQ is the fast acknowledgement and repeat mechanism within LTE. And really, this mechanism dictates a lot of the design challenges involved in implementing LTE, especially in software radio. Above that, you've got the radio link control layer, so segmenting and kind of concatenating packets. It's got the slow repeat mechanism that sits on top of the HERQ from the MAC layer. It operates in 3 modes, so transparent, unacknowledged, and acknowledged mode. Above that, you've got PDCP, which is responsible for packet header compression, ciphering, integrity protection. And then you've got the RRC. So this looks after the connection between the UE and the eNode B. It's the radio link, managing mobility, managing QoS, managing paging, these kind of things. And then above that, you've got the non-access stratum layer. So this looks after the control plane connection between the UE and the MME. So it's the connection between the UE and the core network itself, responsible for authentication, network attach and detach, security mode management, and so on. And this is what the user plane protocol stack looks like for the end-to-end network. So on the left-hand side, you've got the UE with that user plane stack that I just described, moving through the eNode B, the serving gateway, the PDN gateway, and out to your application server. So as you can see, you're moving from the UE to the eNode B, and then you're tunneling over GTPU. And then it's IP through to the PDN gateway, and then out into the wider network. And then the control plane network is the connection between the UE and the MME itself. And so in this one, it's slightly different in that you're going to the RRC layer and the eNode B, and then moving on to the S1AP interface, which runs over SCTP. So this is the original physical layer DSP library that SRS LTE consisted of. And this is really a hierarchy of modules. We've tried to build this to make it as extensible as possible from the lowest level of small granularity DSP blocks, FFTs, turbo decoder, these sort of things. These are then combined up into the physical channels to the PHCH above that, and combined up into individual processes, things like cell search and the downlink and uplink for the UE. And then above that, we have a number of file layer examples. So if you pull the code and take a look, you'll see these file layer examples. They're very, very good for testing and for measurement. Then we've built the full UE stack on top of this. So at the physical layer, we're using the DSP library to build our DSP chains, but we're also building in the MAC with the various procedures required there. This slide really is kind of indicating where we're putting our buffers and how we're doing our threading. These were key design choices in trying to build a system that can maintain the rates required for LTE. And the eNode B stack, so slightly different. One of the interesting things was the move from starting off with the UE. So there are quite a few projects out there that started with the eNode B. One of the problems with starting with the eNode B is that it's quite easy to cheat. So in LTE, it's a real master-slave system. So the eNode B tells the UE what to do. So if you're building an eNode B, it's quite easy to say, okay, we're only going to support this set of parameters, and we're going to leave it up to the UE to follow our lead. If you're building a UE, you can't do that. You have to support all the available parameters, which makes it quite a challenge. But it also means that you're filling in all the gaps from the outset. So then we moved to eNode B, implemented the eNode B. Some of the design decisions we were making, so SRS LTE is written in C, so it's very simple, very portable. The UE and eNode B stacks are written in C++, sitting on top of that. Each layer is implemented as a single class. So we use a fairly clean interface between those classes, so you can see exactly what function calls are going back and forth. One of the objectives was to make it very clear to people who wanted to use and extend the code base itself. And if you pull the code and take a look, it should be fairly clear what's happening where. And we've quite a lot of users that are building on top of this and are extending it and modifying it for their particular needs. So I talked a little bit about the technical design considerations in trying to implement LTE in SDR. And Manuel briefly mentioned yesterday the latency requirements for SDR, and really this is the critical point in trying to implement LTE. So in LTE, the basic time unit is 1 millisecond, is one subframe, and the latency constraints are driven by a 4 millisecond window. And this comes from the HERQ process, this automatic repeat and request. And so you have two scenarios. So the first scenario is where in subframe N, you receive a downlink grant through the downlink control channel, and you're also decoding the downlink shared channel, so the data. And then in N+4, you're required to transmit your acknowledgement or your negative acknowledgement to the physical uplink control channel. So that gives you this 4 millisecond window in which to do your decoding and then to encode and transmit your acknowledgement or negative acknowledgement. And then the alternative requirement is that in subframe N, you receive an uplink grant or a negative acknowledgement on the HRQ, and then in N+4, you're required to retransmit your data on the uplink shared channel. And then you've got the worst case scenario where you have the two of those happening at the same time. So in subframe N, you're getting your downlink grant and your uplink grant or your negative HRQ. Then you've got 4 milliseconds to decode your downlink data, encode your uplink data, and get it to your front end, along with your acknowledgement or negative acknowledgement for your decoded PDSCH. So this really dictates the challenge in implementing LTE using SDRs. And another way to look at it is through this figure where you can see the limitations on performing your DSP and the limitations on how you can parallelize those DSP implementations. So here you're receiving downlink and uplink grants in subframe N. Then you have to move your data, so you have to buffer your data in your front end, move it to your baseband processor, perform all of your processing, copy it back to your front end, and then transmit it the specific timestamp that you have to hit. in parallel, so you can receive subframe n+1, and then you have to do the same process and hit your target for n+5, and so on and so forth. And one of the implications for this is that the maximum useful pipeline depth is 3 stages, so 3 threads is fairly optimal for this sort of setup. If you have more cores than that, then you can start thinking about dividing your uplink or dividing your DSP chains into multiple stages. But things like dividing your uplink and downlink into 2 threads isn't particularly efficient because you've got one thread waiting for the other and you lose those parallelization gains. And this is a rough kind of description of the timings that you're facing when you're using a USRP, for example, as a front end. So you're looking at a 4 millisecond window, you've got 1 milliseconds for RX buffering, half a millisecond for transfer, you've got 2 milliseconds left to do all your downlink and uplink processing, and then you've got half a millisecond again for host to USRP transport. And so this can be quite challenging. And obviously, as Manuel mentioned yesterday, the move to 5G is going to make this even more challenging with the reduction in those latencies. So LTE, the processing requirements for LTE are pretty high. This is a kind of a rough description of the requirements for each of the various standards as they've progressed over time. And if you break that down and look at, for example, the receive flow for an LTE DSP PHY chain, you'll see that it's dominated massively by the turbodecoder. So you have an order of magnitude greater computational complexity in the turbodecoder. So if you can crack that nut, then you can typically achieve the rates that you want to with LTE. And so in optimizing your waveform for LTE, that's really the starting point. And we use 2 major tools to achieve this, so SIMD, obviously, and a lot of pre-compute. So we typically target GPPs, so you can pretty much assume that memory is almost free on those platforms. So we pre-compute as many signals as possible and use lookup tables wherever possible to hit the kind of throughputs that we want to meet. And then we also use SIMD intrinsics whenever possible. So our PHY layer is almost entirely integer arithmetic DSP. The only piece that isn't right now is the FFT, and that's because we use FFT libraries that use floating points, and we've yet to find a good integer FFT library that outperforms those. Just after I'd written the slide deck, one of my colleagues came back with an implementation on Slack and said, "Hey, I've just written an integer FFT library that outperforms FFTW. So watch this space. That may be being released before Christmas." Okay, so this is just a breakdown of some of the computational complexity as you scale up in throughput. And as you do scale up in throughput, you'll see that the turbodecoder, just for one iteration, really starts to dominate the processing chain there. So it just kind of reinforces that statement. In optimizing the turbodecoder, we used 18-bit integer arithmetic and SSE4 originally. We've moved on to AVX, AVX2, AVX 512. And so we're parallelizing and computing all of those trellis states in parallel. And I mean, the implementation is completely open source. So if this is something you're interested in, pull the code and take a look. And this is the sort of execution time we're getting for the PDSCH only at 20 megahertz. So we're getting a fairly nice linear execution time as the bit rate increases there. Okay, so that pretty much sums up the talk. One thing I did want to show you was this is a product which we've also released. So we do, as a company, we do various things. We do open source, we do R&D projects, we do commercial projects, and we also do standalone products. This is one called AirScope, so it's an LTE sniffer. So this runs on an off-the-shelf PC or laptop, uses an RF front end like the USRP or any of those that are available. And we've got 2 running, so this is just we've one deployed in Dublin and one deployed in Barcelona, and these are just sniffing local cells. So it'll listen to the downlink control channel of a local cell, and it'll tell you all about what's happening within that cell at any given time. So things like the number of active users, the amount of data that's being generated in the uplink and downlink by those individual users, as well as cell-wide statistics like SNR, RSRP, RSRQ, path loss, and so on. So on the top graph here, we've got the aggregate downlink and uplink throughput for the cell. On the bottom, we're picking the 20 most active users and just tracking them over time and looking at how their data consumption and generation changes. Okay, so that's all I have. Any questions?
Hi, so this is not necessarily this actually is not a file layer question, but there's a lot of different LTE kind of open source file layer solutions for different types. One of the issues at this point is finding a good EPC, and I saw that you guys plan to make one. Is that going to be something that you're going to make possible to work with some of these other, open LTE front ends, so that, because that's the thing that's really missing.
Sure, yeah, absolutely. So our objective with the EPC is we're not that interested in the internal interfaces within the EPC. Our objective in building and open sourcing an EPC is to make it possible to have an end-to-end network. So we'll have the standard S1 interfaces. We're probably not going to expose all the internal interfaces. It's probably going to be a single application, and then obviously an IP interface out to the outside world. But we are very interested in connectivity with other projects and other products as well. So we're testing against a large variety of eNode Bs. So we've been doing that with our UE for quite a long time. We have been testing with a variety of different EPCs, so our eNode B, various other different EPCs. And we're actually in the process of building an over-the-air test framework where we can do nightly over-the-air tests with a lot of these other different implementations to make sure that we're maintaining support for them and maintaining compatibility.
Just wondering if you had ever thought, or if it's even possible to offload some of the turbo decoder into the FPGA?
That's something we have thought about. It's not something we've worked on too much just yet. Some of the work that Intel is doing with integrating the FPGAs could be very interesting for that. So we're keeping an eye on it, but we're not actively working on it right now.
So if a solution comes up, you might try
Yeah.
see it.
Yeah.
Sorry, the microphones are coming to you.
Hi, I enjoyed your talk. I'm an amateur radio enthusiast, and a lot of talk, of course, with the hurricanes at the moment. Everybody's talking about FM simplex radios. Basically, when the Armageddon comes, the people that will survive will be the insects, the birds, and people with FM simplex radios. The other thing I'd also like to know is how well does, if you're a first responder and you're responding to an incident in a building full of metal, concrete, metal structures, how well does an LTE signal penetrate within the building to allow people to communicate with each other? Are there any hindrances to LTE in that respect?
Sure, yeah, definitely. And I mean, the answer to that is it depends. It depends on how you deploy your network, and depends on what frequency you deploy network at. But you touched on an interesting topic. So the use of LTE for public safety, there is some controversy about that in itself. And we've done quite a lot of work with Roger Jover at Bloomberg, who's a security researcher, looking at the kind of vulnerabilities that LTE has, specifically for jamming, as well as other fuzzing sort of attacks. And one of the objectives in creating this R&D platform is to allow people to test those out and to check those out. We're already providing tools to researchers. Bloomberg and Virginia Tech have some very interesting research that they just published on this topic, but it's definitely of interest to us.
Hey, Paul, can you hear me?
Hey.
It's on, right? Okay. So just speaking in terms of technology trends in the FPGA and turbo decoding, you might be interested to know, and folks in the audience might be interested to know, that the RF SOC from Xilinx, there are options where they've actually implemented a hard FEC block in there. It's a soft decision FEC, though, so it makes soft decisions, and it supports both turbo decoding and LDPC, which could be the new standard for as part of the 5G standards.
Yeah.
So I think the whole world is converging towards there. FPGAs are getting there finally as well in terms of just having hard blocks, which will do that extremely efficiently, ASIC-like performance and efficiency. So I think that's the clear trend here.
Thanks. Yeah, that's very interesting. I mean, that's the other challenge with 5G, the move to LDPC codes. it makes parallelization very, very difficult. So latency and LDPC are really the big challenges for 5G for us.
All right. Thank you very much, Paul.